Thank you very much, Anna, and good morning to everyone. We have a very exciting lecture ahead of us. We already met the speaker yesterday because he took part in the panel discussion. It is Hugo Duminil-Copin. He is a French mathematician specializing in probability theory. He has received many prizes. Of course, the most prestigious and the reason why he's here is the Fields Medal that he received last year in Helsinki. Let me read the brief citation. He got the Fields Medal for solving long-standing problems in the probabilistic theory of phase transitions in statistical physics, especially in dimensions 3 and 4. We like these dimensions. We're looking forward to Hugo. Please, the stage is yours.
Well, congratulations for having come on time for the bus this morning. I understood yesterday evening that some people were not so optimistic about making the bus, so very good. Actually, I didn't check if they are here. So I realized yesterday by listening to other talks that maybe I didn't go on the, telling you about the whole story, how I came here, blah, blah, blah. I thought that for the wise advice, wait for 20 years when I would get to the wise level, because I didn't reach it yet. So it's going to be a very scientific talk. I'm going to tell you not really about my own research, but my area of research in general. And in order to do it, I will focus on one example which I think illustrates pretty well what we do in our area, which is the Ising model. So let's start. There will be many names. I like to scare people a little bit at the beginning, just it's natural selection. So there will be a few words here that I will explain, but some of them I will just brush through it. But my goal is really to give you a high-level panorama of the field. So in my field, we start with a model. And very often, in most talks in my everyday life, the person in front of me usually throw at me a definition of the model. I have no clue where it comes from, why on earth somebody would be interested by this. What we do from there is not so clear either. So what I'm going to do in the first part of the talk is telling you how you cook up a model, actually a mathematical model for a physical phenomenon. And as I said, I will take this example of the Ising model. So when you cook up a model, you start by an experience. You have a physical phenomenon you want to understand. So here is me doing an experiment. The physicist in my lab, in my university, forbidden me from using something that is more dangerous than the light. So it's going to be a little bit long. So the idea is that you take a magnet and you hit it. Okay? And something that you may not know is that when you hit it at a certain point, it's going to happen something dramatic for this poor magnet, is that it's going to lose magnetization here. Boom. It failed because it's not a magnet anymore. There is a temperature. It's called Curie's temperature. It's Pierre Curie who, in physics you have to be careful, so who discovered, or rather rediscovered, the phenomenon in the end of the 19th century. And he noticed that whatever the magnet, whatever its composition, there is a temperature at which it loses magnetization. And that's what we would like to understand mathematically. So this is a phenomenon. Now, what is the first step of building the model? Well, the first step is going to be first to define, sorry, we are mathematicians, we define things, to define what we mean by a magnet in the mathematical sense. So let's try to get there. So we are going to be inspired by physics. In physics, we know that magnets are made of small dipoles. We call them spin. You should think physically it's related to the magnetic moment of electrons in atoms, but this is not relevant for us. Just, we are going to think that a magnet is made of all these small constituents, and we are going to make some assumption on these things. The first one, it's Mark Katz that always tells us this, is be wise, discretize, which I think in a computer science mixed audience with mathematicians, it's something that most people will relate to. So let's make it a discrete model by forcing the spins to be on a regular lattice, on a regular graph. you may think this is a catastrophically reducting assumption. It's not. In fact, you could do most of the things on something non-regular, where maybe they are randomly positioned in the space. It's just going to be more complicated, and I can already tell you it's not that simple when it's on a regular lattice. So these spins will be on a regular lattice. And the second assumption, this one is much worse, but let's make it nonetheless. We want to simplify reality, right, to make a caricature. So we are going to assume that these spins, they are like small magnets that point in one out of two possible directions. They either point north or south, but there is no other direction that they can point on. This is not what is happening in reality, and there is an interesting question of releasing this assumption, but in the Ising model, this is the assumption. So that's our magnet. Magnet, if you want, in the mathematical sense, it's just a function from the sides of a graph, of a regular graph, into plus minus 1. I mean, we are mathematicians. Huh? North, south is plus minus 1. Once you have the magnet, what do you want to measure on this magnet, right? Well, you want to measure its strength. And the strength of the magnet here, it's going to be called the magnetization. It's just going to be the average spin. I'm just averaging the spin, and I see what I get. If it's close to 1, it's kind of a magnet that is strongly pointing north. If it's roughly 0, because there are as many up and down spins, then it's a demagnetized, basically. So that's our magnet and what we want to measure on it. First step of cooking the model. I mean, this is very arbitrary. Huh? You could try to change a little bit the definition. You could try to change a lot the definition and see how it impacts the model. The second thing we do is something that, I mean, maybe you are all already convinced, but still I'm going to go through the open door. And when we do the physics of the infinitely big, like cosmology, general relativity, we very often manipulate very few elements. If I speak about the solar system, there are 9 or 10 elements, depending if you are my age or yours. But Pluto is a planet, I'm sorry. It will remain a planet. So 10 elements, it's not that big. It's already very complicated to understand what happens, but OK, it's 10. If you look in the infinitely small, if you see, for instance, Alain Aspect, the last Nobel Prize in physics, he works on ultra-cold atoms. And in the traps where he cooled down these atoms, there are very few atoms that are actually interacting. And so there as well, sometimes you can restrict to very few atoms. But when you do statistical physics, when you are studying the physics of our scale, the systems you are looking at are enormous. There are like if you look at particles in this room, like there is a huge number of them, huge being really big. So in this case, there is basically only one way to go around it, is to use probability, to focus on typical behavior rather than explicit behavior. And that's what we are going to do. We are going to introduce a little bit of randomness, and in statistical physics, to introduce randomness, there is almost a dual concept, which is the energy of your system. So for a magnet, I want to see what is the energy of the magnet, and we are going to do something pretty natural. We are going to say small magnets, like small dipoles, they want to be aligned, exactly like big ones. So if they are aligned, it costs a certain energy. If they are disaligned, it costs more energy. So for every bond for every edge in my graph, I'm going to put an energy which is minus sigma x, sigma y for the edge, where x and y are the endpoint of the edge. So it's +1 if they disagree, -1 if they agree. So it's really telling us that the model is kind of ferromagnetic. It wants to have aligned spins. I take the energy to be just the sum of all these small energies along bounds. And from there, I can define a probability measure, which is going to tell me that the bigger the energy, the smaller the probability. Okay, so the probability of my magnet is going to be proportional to exponential of -1/t times the energy. And t here, it's not a randomly chosen letter. It's going to be considered as a temperature, right? The temperature is a level of excitation in your system. So here, the larger the t, the smaller the 1/t h of sigma, so the less you care about the energy. In fact, t equal infinity, you are looking just at a randomly, uniformly chosen magnet, you don't care at all about the energy. When t tends to 0, in this case, you have two magnets that could occur typically. It's going to be all +1 or all -1. These are the minimizers of the energy. Is it fine for everybody? Yeah. So good. I will say that all people who said that are fine, and all people who didn't are sleeping. That's, that's what I will say. Okay. Very good. That's our Ising model. It's a randomly chosen magnet in the sense of a function from the sides into ±1. From there, you want to measure the strength of the magnet. And now that we have a random object, we are just going to average the magnetization of a single magnet. And here, immediately, what you see, and you are going to think, OK, this is going to be even more boring than I expected, this talk, is that you immediately get 0. Why? Because a magnet and its full reverse, when you reverse all the spins, they have exactly the same probability, right? And they have opposite magnetization. So average magnetization in this model is 0. And that leads me to the third step in the building of a model, is that usually you want to break the symmetry in your model. A magnet is always living in a magnetic field at some point, right? Here, you want to implement the fact that there is not a full symmetry between pluses and minuses in my model. So there are different ways of doing, and the one I chose, it's not the physical one, but it's equivalent to the physical one, is to say that if I am in a magnetic field, in some sense, the spins on the boundary of my magnet, they should point in the direction of the magnetic field, say +1. If you are wondering why there is a red dot, so at the beginning, I thought I would explain the dynamics that there is behind the model to explain why you have this probability. Then I realized I don't have time to do it. But I forgot to remove the video. And I realized that this is the point where people listen the most. They are like, no, where is going to be the red dot? Where is going to be the red dot? Oh, no. So then I'm leaving it. And every single time I'm like looking at people trying to follow the red dot. So anyway, we are cats at the end, right? So I break the symmetry. The spins on the boundary must be pointing +1, no choice. And I just look at the same measure, just conditioned on the fact that I'm always looking at magnets where the boundary sides are +1. And notice that when I do that, the full reversing argument doesn't work anymore, simply because I cannot reverse the spins on the boundary. So when I look at the average magnetization here, I'm going to get something which is, in fact, it's non-zero. It has no reason to be 0 anymore. And in fact, you can even prove that it's strictly positive. Again, it's kind of natural if you are forcing spins to be +1. It's kind of, if you think this magnet analogy, guys rather want to be +1 than -1. They want to be aligned. But the interesting thing is not so much that this thing is strictly positive, is that we are mathematicians, and mathematicians are much more afraid of numbers than they look at first sight. So a big number for us is very scary. So what do? We react like epidermically by saying, oh, so if it's big, it's infinity, right? So that's what we are going to do. We are not going to, we think of a magnet as a huge collection of small dipoles or small spins. So what we are going to do is we are going to take the size of our graph to infinity and look on the full lattice ZD. So when you take the limit of this quantity is strictly positive, but the limit has no reason to be strictly positive anymore. It's larger or equal to 0. And the question is exactly going to be, is it 0, or does it remain strictly positive? This quantity, by the way, is called the spontaneous magnetization, because if it's strictly positive, the interpretation is a little bit like removing the magnetic field and then seeing whether your magnet remains magnetized or not. If it remains magnetized, then it's a true magnet, it's a ferromagnet. Otherwise, it's called a paramagnet. Yeah, so taking the infinite limit and breaking the symmetry are the two last typical things you do in building up a statistical physics model. And from there, we have our model. So we have our model, very good. What do we do with it? Well, we want to explain the experiment, so we want to see whether there is a phase transition or not, so a brutal change of behavior or not. And here, the interpretation will be, I want to look at the temperature
and see whether it has an impact on being a magnet or not, which here I interpret as whether m star of t is strictly positive or equal to 0. Okay? On the left, I said it's a ferromagnet. On the right, it's a paramagnet. And in the middle, it's called the critical temperature. So now you can go to a statistical physicist and say that you understand everything he does, because mostly the thing is going to be to try to understand what happened at the critical temperature. So, very good. But at this stage, it's not even clear that the critical temperature exists in the sense it may be 0, it may be infinity, there may be even like, exchange of ferromagnet, paramagnetic phases. I mean, there can be a lot of things. And that's the point where I like to go to the story, the history of the problem, because it's a fairly interesting one. So the model was introduced by Lenz and not Ising. As often in physics, never, this is one of the rules about it. You never call a model after the person who invented it. That's very important. Otherwise, you are called a mathematician, and you don't want that to happen. So Ising was not the inventor. He was actually the PhD student of Lenz. And what he did is the following. He studied the one-dimensional case. Imagine a chain of small dipoles. And there he proved something very boring in some sense, or at least he's proved that the thing is behaving in a boring way, which is he proved that the critical temperature is 0. Meaning as soon as you tune the temperature, as soon as it's not 0, then you always have 0 spontaneous magnetization. You don't have one-dimensional magnets. It's almost an exercise that I could give you. For people who are bored, you can try to think about this problem and come to me by the end. No, don't do that. But by the end of the talk, you may even have the answer. And then you did the PhD of Ising. But to be Ising, you need something more. You need to make a prediction. And the prediction that Ising did is the following. He said, well, if it's like that in 1D, it should always be the case. It should be that whatever the dimension, Tc is 0. And that was catastrophic for the model because it was really saying there is no magnet, at least in the sense of this model. So it's a very poor model for magnetism. Fortunately, so even went to Lenz and to Pauli to say, oh, it's a little bit disappointing, right? The model you gave me and that my name will be remembered for is not a good model. But the good thing about it is that it was totally wrong. It's always strictly positive, except when you are on the line. So you cannot do a more wrong prediction, basically. It's impossible. At some point, people thought, OK, we know in dimension 2, 3, 4, and more. But actually, very recently, we even proved that when you take fractal graphs of dimension that doesn't have to be an integer, even if it's 1.00001, it's strictly positive. Too bad. But you see, it's a good way to get your name remembered. So Hans Ising forgot about, left academia and discovered 30 years later that he was so famous in some sense. A second thing that was probably much, here I'm making a joke out of it, but you always have to go back to the moment where it was done, and these were already very nice achievements. But there was something much worse for the model than this prediction that nobody truly believed at the time, is that Werner Heisenberg, the same as Heisenberg uncertainty principle, introduced another model of ferromagnetism. And this other model of ferromagnetism was really based on quantum physics. And the 20s and 30s, this is one of the golden ages of quantum physics. And the Ising model is not quantum at all. There is no, it's a classical model, the most classical model you can imagine. This other model is really much more physical. So in some sense, why caring about a model that both doesn't give you the right prediction and is not even related to the right physics? But what happened is that Peirce, in 1936, proved that indeed Ising was wrong. You always have Tc strictly positive. You always have a phase transition. But more importantly, Peirce also proved that many of the models that were cooked up at the time, for instance, for binary alloys or for cooperative phenomena, all these models, in fact, in disguise, they were exactly the Ising model. So a single model can explain different phenomena. Maybe not very accurately, but can describe different phenomena. And this is exactly the game of theoretical physicists and mathematical physicists, is you want to take the right model in the sense that you don't necessarily want the most precise model, because there is very good chance you will not be able to say anything about it. You want to find the right, focal, if you want, to be able to study the model and say non-trivial things. And at this right focal, usually there is something nice happening, is that you don't distinguish between many different phenomena. And so you create paths between different phenomena. You create a common language to study different phenomena, which is something that you may not be able to see when you are the physicist really doing the experiment, in some sense. And I will come back to that later, because you will see, in fact, it's a little bit the goal of my talk to give you an example of a link between two completely different phenomena. Okay. The very important thing about the Ising model came a few years later. It was Lars Onsager who proved it. And what Lars Onsager did, so he was a chemist. I mean, of course, at the time, theoretical chemists were basically mathematicians. There is no big difference between the two. He got the Nobel Prize in chemistry, not for this work, but this work is as important. So what he did is that he proved that in 2 dimensions, so if you look at 2-dimensional magnets, you can compute things explicitly, which normally you have 2 reactions when you are a mathematician. Either you are super happy, because, oh, yes, I have a closed formula, or you are super disappointed, because, well, if you can compute, it's too easy. So Lars Onsager computed something. I put the formula here. I mean, I like to put these formulas even in front of very general public, because you can see the panic in the eyes of people. What are these signs? The person is going to... Okay. So the formula is saying something not that complicated, is that the term on the left, it's the typical energy per unit of volume of a magnet. No, you have a magnet, you sample it at random. What is the typical energy of the magnet? Well, what Lars Onsager says is that there is a formula for it in 2 dimensions. It's really an absolutely beautiful result. It's one of the most important results in statistical physics. It was it's a difficult proof. It was drastically improved by one of his PhD students, Breuer Kaufmann. Even the improvement is still difficult. And people tried many different approaches, so you can prove this result using combinatorics, algebra, analysis. I mean, there are like tons of different ways of doing it. I'm mentioning it just to say that this is also one thing you recover, and that is very nice about this area of mathematics, is that it's at the crossroad of many other areas of mathematics. And just for the story, there is a paper that is entitled The 399th Solution of the Ising Model, which is a 399th way of computing this thing. It's a slight exaggeration, but I think 20 is probably a good estimate of how many different ways there are to prove this. I mean, I introduced these 3 energies, this typical energy, but let me mention that you can do much more than that. Chen-Ning Yang, the same as Yang-Mills, Lee Yang, Yang-Baxter, I mean, one of the most influential theoretical physicists of the 20th century, Nobel Prize winner in physics. One of his early work was actually to take the technique of Onsager-Kaufmann to push it really much farther, to prove that you can even compute the spontaneous magnetization, and you get this formula. So I think now this formula is right, because actually for a year I just showed the wrong formula without anybody telling me anything, me included, so myself included. So I noticed, so you have this explicit formula, and from this formula, for instance, you can even compute the critical temperature. So you can explicitly compute the spontaneous magnetization. just for, I mean, Chen-Ning Yang said that this was the most annoying, difficult, disgusting computation he made in his life. So I'm not recommending that you should try to do the same. Okay, so in 2D, you can do everything you want. You can even locate the critical points. Seems easy. Well, it's not, but at least it goes very far. But it's really on the square lattice. Because there is something that all these people use. It's called integrability. And it's a very, very, very specific property of two-dimensional models. It's something that goes, like, it's cross, again, it goes to very different areas of mathematics. It's related to algebra, to the Yang-Baxter equation, which is something that you usually hear in integrable system in very different areas of math. But this integrability property, it's very, very fragile. I mean, fragile to a point where if I'm saying, okay, maybe my sides, I'm a physicist a little bit, let's say in the morning I'm a physicist, and I'm a little bit annoyed because, I mean, why would it be that two small spins in my systems only interact if they are fully nearest neighbor? This is kind of, I mean, why wouldn't you interact with the next nearest neighbor a little bit? Just a little bit, but why? You would not do that. So let's say you want to do a slightly more physical model, and you want to introduce some next to nearest neighbor interaction. Even like tiny, you don't say it's minus sigma x, sigma y, you say it's minus 0.0001 sigma x, sigma y, something extremely weak. Whatever the weakness, everything breaks. Everything. You get zero integrability. It's not that you can salvage anything. It disappears. Okay? So that's very annoying mathematically because it's, or physically, I mean, well, it's both annoying for math and physics because that means that your argument is in some sense not physically so relevant. It's not really explaining the physics behind it. But unfortunately, sometimes you just have what you have. And for many, many years, in some sense, the understanding of the two-dimensional model was like really much better than the understanding of, say, the three-dimensional model. Exactly for this reason, the two-dimensional model is integrable, not the three-dimensional one. Many people try to solve the problem by saying, let's prove that the three-dimensional model is also integrable, that you can compute everything. But this is an open problem, and I would definitely not recommend it because just I don't think it's integrable. So, and I think most people actually agree, physicists included, that a priori there is no reason that nature would have given this gift to us. Okay, so what do we do in 3 dimensions? And that's a little bit what I'm going to tell you now by focusing on the next question. So the next question, once you have proved that there is a phase transition, let's say Peirce proved that there is a phase transition in any dimension, you didn't need integrability to prove that, what do you do next? And the idea there is that there are 2 kinds of phase transition in nature. You have the continuous one and the discontinuous one. If you take water and you bring it to 0 degrees, it becomes ice. And there is this very funny thing if you want to do an experiment with your kids, is that, or your friends, sorry. I see that there is maybe a generation gap here. Is that you put a bottle of water, you fill it completely, you put it in the freezer, and it's going to explode because simply ice is taking 10% more basically space than water. Okay? It's actually even more drastic at 100 degrees. When you get to vapor, then it's 10,000 factor. Unfortunately for us, it was the principle of vapor machines, right? Machines that are based on vapor. And the point is that these phase transitions are discontinuous. If you plug the volume, there is a jump, right? A discontinuous jump. But there are phase transitions that are not like that. And in particular, if you take magnetization of a magnet, you plug it as a temperature. You take real-life magnets. These are real-life magnets. In fact, this is taken from Curie writing for the Academy of Science, where he describes the Curie temperature for the first time. He doesn't call it the Curie temperature. But so what happens is that when you plug it, you see that there is a continuous, there is a singularity in the sense that it doesn't seem to be differentiable or anything like that. But when you take bigger and bigger magnets, you see something that looks, in fact, continuous. Okay? And in 2D, we have an exact formula. If you plug the exact formula, you see that it's continuous and that it behaves like Tc minus T to the 1/8, in fact, when T approaches Tc. So in 2D, thanks to the formula, you can prove immediately that it's continuous phase transition. You can even ask your small child to do it when he's 5 or 6. I heard that some people who did work very early on, so I'm careful not to. I'm not one of those persons, but okay. So continuous in 2D because of the exact expression. What happens in 3D? And surprisingly, it's really question 2 in your exam at the end. Question 1 is there a phase transition, meaning Tc, is it 0 or plus infinity or between? And then question 2 is this. And surprisingly, well, question 2 remained open for 90 or, almost 100 years. And the reason is that, what's the tool you are going to use in 3D? You cannot hope to compute things explicitly. What do you do? So that's what I'm going to discuss in the last minutes of this talk. How do you prove the continuity of the phase transition? So this is a theorem we obtained with Michael Eisenman and Vladas Sidoravicius. And maybe the proof is even more interesting than the actual result. But we can prove that the spontaneous magnetization at the critical point is 0. And in fact, it's very easy to get from that it's a continuous function even of T. The only way it would be discontinuous is if it was non-zero at Tc. Okay? And let's speak about the proof. I like this moment because people are, no, I came here, I woke up, it was under the agreement that I will not see a mathematical proof. But yes, there will be one, an idea of the proof. In order to tell you a little bit about the proof, because that's where the juice lies, let me introduce another player in my game. I mentioned the spontaneous magnetization, that's the key player. But let's think of another quantity that is interesting in random systems, is to look at correlations between different parts of the space. How a part of the space is influencing another part of the space. And the quantity here that I'm going to look at is how a spin somewhere is influencing a spin somewhere else. Okay? So I'm going to look at the average of sigma 0, sigma x, which is exactly this correlation between the position of the two sides, between the spin at the two sides. So I just gave the formula, but it's not so important. It's really I want to compute the correlation between the two things, or see how it behaves. And the first thing you can see is that when you take two spins and you take them farther and farther away, they are going to behave more and more independently. It's kind of natural. They feel each other less and less. Okay? And so in particular, what you can prove is that it converges when x goes to infinity. So you fix 0, you let x go to infinity. It converges to the spontaneous magnetization squared. Why? Because in fact, the average of a spin, I define the magnetization as kind of a space average. I'm averaging on the spins. But in fact, I get from ergodicity that it's the same as averaging one spin. So this correlation, it converges to the magnetization squared. But there is another result. It's much less obvious, but I don't want to be really discussing this, and it's something that we know for many years. It was known before I was born, which in my case, I consider it many years. It's that, in fact, the spin-spin correlation tends to 0 when you look at T equal Tc. So when you look at the critical points, the correlations tend to 0. But that seems to be trivially saying that the spontaneous magnetization is 0. Right? Except that there is an except. There is a catch, which is that I was careful not to tell you what measure I was taking. And remember, there was a measure that was without symmetry breaking and a measure that was with symmetry breaking, where I was forcing the spins to be all plus on the boundary. And these measures have nothing in common a priori. They are not the same measure a priori. So what happens is that if you want to conclude the theorem, you need to prove that the two measures are the same. And this is something in physics. I mean, when you have a discontinuous phase transition, you have what we call, several Gibbs states, several stationary states for your system. If you look at zero temperature, in fact, when you get to zero temperature, to zero Celsius temperature for water, it's not that it's immediately getting for liquid water to ice, right? It's going to be a slow process. You need to wait for your Coke to be at the right temperature, right? And the reason is that there's going to be a coexistence of two pure states, liquid water at zero temperature, and ice at zero temperature. There are two possible states of matter for water at zero temperature. If you want to prove the phase transition is continuous, you need to prove it's not possible to have these two different states. There is a unique state of matter at the critical temperature. That's exactly what we need to do here. Okay. I can see already that people are a little bit dead. So it's it's a moment where I had the best ovation in my life a week ago. It was very funny. It was better than ICM, I must say. Sorry for mathematicians, but there is a saying in French. We call it the trou normand. The trou normand is this thing in the middle of your dinner. They bring you some Calvados, like some heavy alcohol. You drink it, and it's supposed to, help you go back for a second dinner, basically, for the second half of the dinner. And in French, I use this denomination. So this is a trou normand. It's going to help you for the next half of the talk that is going to be 5 minutes long. But this is just a small detail in my story. But I did that in Le Havre, which is in Normandy. And then I say, so now it's time for trou normand. And like everybody started, trou normand. And, so, here it's not that working so well. Maybe there is there is an equivalent here. I should ask you before the talk next time. But anyway, so that's our trou normand in some sense, our detour through a completely different story. So forget about what I said. If you were not interested, think of the following. How do you model a porous medium? Something that is porous. Let's say, a porous stone or coal. How do you model it? So you can model it, again, using randomness because you don't want to break it, or it's made of, it's very complicated inside. So you are going to model it as a random labyrinth or a random graph, say. That is going to tell you, where water or gas or whatever you put in flows. So take, for instance, a simple model, take the square lattice or take ZD, any lattice you want, and for each edge, choose it to be red with probability P and gray with probability 1 minus P. And you do this independently for every edge. It gives you a random subgraph of the original graph, and you can look at the connectivity properties of this graph, right? This one, it's a second cooking of a model. It's even simpler than the other one. And this thing is quite interesting. Look at what you get, for instance, when you take P equals 0.49. It's on the left. Oh, whoa. So it's supposed to be a beautiful picture. It's a little bit blurry. It should not be blurry. But on the left, it's P equals 0.49. And on the right, it's P equals 0.51. So P is extremely close, right? It didn't vary so much. And the colors are the different connected components of your graph. And there is no bug in the picture. On the left, you have only tiny connected components. On the right, you have one huge connected component, the red one. There is a phase transition again, a sharp change of behavior in your system that in fact happens exactly at P equals 1/2 in this case. So if you would look at infinite systems here, the phase transition would be that below the parameter PC, which would be your critical parameter, there is no infinite connected component almost surely. And as soon as you are strictly above it, you will have an infinite connected component almost surely. So complete change of behavior. So it's really a different model. And in fact, just to mention, Rosalind Franklin, from the DNA story that I don't want to get into, she did actually study coal many years before the mathematician came up with the model. The model dates back to 57, and I think Rosalind Franklin's work is in the 40s, early 40s. So what she did is that she looked at coal, and depending on the size of the molecules, she was trying to see how it percolates through coal. And one of the goal was to try to measure the porosity, the density. I don't remember exactly the quantity, but something about the inside using this trick of pumping in gas with different size of molecules. It was the first experiment on percolation in some sense. So you will tell me what's the connection between percolation and the Ising model. On one side, you have a model for ferromagnetism. The other side, you have a model for porosity. Well, it's that in fact, you can explain the correlations in the Ising model in terms of a percolation model. It's like you can encode how much the spins speak to each other by a random graph, which is going to connect the two spins if in some sense they correlate, and do not connect if they don't correlate. So you can, for instance, prove that the spin-spin correlation of your Ising model get rephrased as probability connectivity for a good percolation model. It's not going to be the simple model I explained before. It's called Bernoulli percolation, the other model. But you can do it in terms of a percolation model that we call the random current representation. By the way, I didn't come up with these things. This is dating back a long time ago. I will tell you what I did on this. But you see, as often when you start having a connection, the connection goes much faster. You create a creature, but the creature starts walking and you start panicking. So here it's a little bit the same. The connection goes much farther than you think, and in particular, you can even measure the difference between the correlation in the plus state and the correlation in the state where you didn't break the symmetry. And the difference between the two is going to be related for the same percolation model to the probabilities that both 0 and x are connected to infinity. Don't ask me why. I mean, you have to do some math at some point. But the good thing about it is that notice that in the previous picture, on the right, on the previous slide, the red area, the red connected component was overwhelming, right? It was almost everywhere. And in fact, what will happen is that when there is an infinite connected component, it's unique. And here you can prove the same for this model. It's unique. But if 0 and x are connected to infinity, then they must be connected together. They are in the same connected component if there is only one. But then 0 connected to x, it's what I got above. So I can bound from above the plus correlation by twice the free one. And then I can use my argument that this thing tends to 0 and this thing tends to magnetization. So here, I mean, of course, I'm lying to you, which is completely obvious. I'm allowed to do that. If you disagree, well, that's the same price. But I'm not lying so much, in the sense that this is really the core idea behind the proof is you rephrase, you get your dictionary between two different languages, and when you rephrase in the term of the second language, then things become just a matter of drawing things almost. Okay? So that's the end, basically, of what I wanted to say. Oh, why is there a blank thing? Oh, that's my research. Okay, so about my own research, that's to remind me, please. So I didn't make the connection. What I do actually for a living is the following. So I arrived in 2008 in academia as a young researcher, and people asked me to prove very difficult things that I still didn't prove. But there was one thing that was bugging me when I was looking at percolation, is that we understood very well percolation when the state of the edges are independent. Exactly the percolation model I introduced, the Bernoulli percolation. There, if I tell you the state of one edge, I mean, because I'm flipping an independent coin for the second edge, I get no information on the other edge. Now, if you look at the connection with the Ising model, you can easily believe because of the fact that it's ferromagnetic. If I tell you the direction of one of the spins, clearly it gives me information on the neighbors because they have a tendency to align with it. So of course, when you do your mapping to a percolation model, your percolation model is going to be dependent. If I tell you the state of an edge, it's going to give me information on the state of other edges. And in fact, many percolation models that were known to be connected to other phenomena in physics, they were dependent percolation models, not independent ones. And that was really annoying me because I was facing this and I was like, we have this beautiful proof, this beautiful theory of percolation, Bernoulli percolation, but the models we want to use are all dependent. So I kind of took my small stick and started trying to re-go through the most elementary results of percolation theory to try to build a theory that would be working for dependent models. And it worked much better than I thought. Let's face it, if you tell me, oh, I already saw that I would get there, it's not at all the case. I don't think that much. I was doing small steps, but it happened that we got to an understanding of dependent percolation models, not all of them, but many dependent percolation models that allow us to have this kind of application, for instance. We can study this random current representation and get information on the Ising model. So that's a blank, that's my work. And just I finish on 3 other examples of percolation models. On the top, it's my favorite one because it's related to many. So it's a dependent percolation model that is related to many different phenomena. It's called the FK percolation. You can have things in the continuum. Here I'm sampling random balls, for instance, just to say that if you don't like discrete, I can still, talk to you. It's fine. And on the right, it's, for instance, these are the nodal lines of the eigenfunction of a random operator, basically. It's not exactly that, but it's called monochromatic random waves. But to say that you get percolation problems out of many different things. And here, for instance, out of trying to solving the equation, looking at the eigenvalues and the eigenfunction of the Laplacian, for instance. You can cook up very interesting percolation models out of it. And there is a lot to be done. So let me just conclude in one sentence for just a problem for you, because I work, so you should work a little bit. So problem for you, just to tell you that in statistical physics, you can state results that are statements that are simple but hard to prove. Bernoulli percolation, you all understood? Every edge, open with probability P, close with probability 1 minus P, independently. Take these 3, okay? On these 3, there is a critical point, again, PC, that is distinguishing between no infinite cluster strictly below, infinite cluster strictly above. Question, is there an infinite cluster at PC? This is the biggest open problem in our field. If you solve it, don't remember to give me a head up first. I want to learn the proof before the others. Okay, I'm very keen. I really want somebody to solve this, and I would be very glad if somebody here has an idea. Thank you very much for your attention.
Thank you very much, Hugo, for a great talk. We have time for a couple of questions or comments from the audience. One in the back. We have a microphone.
Do you hear me?
Yeah, we can hear you.
Okay. Are the techniques different between dimension 3 and 4? So did you have to invent new techniques for dimension 4 and you use for dimension 3?
Okay, so is the treatment different on different graphs? So the link to the percolation model is true on any graph. You don't even need regularity. It can be useful on very large graph, random networks, everything you want. So in particular, the Ising model is sometimes used for cooperative phenomena, and it's used on graphs, that look more like the graphs you get in social networks or things like that. The link is also true. Then the question is how you study the percolation model, and that can differ a lot depending on the dimension. And there is something a little bit funny about statistical physics, but that's also what makes it mesmerizing, is that in dimension 5 and more, things become much simpler, really much, much simpler. In fact, the model becomes what we call Gaussian. For people who did a little bit of probability, Gaussian processes are simple compared to the others. then when you go down to 4 dimensions, it's like one level of difficulty more. So in particular, one other result that was mentioned, you say dimension 3 and 4, one result we proved with Michael Eisenman is to prove that the 4-dimensional model was Gaussian, also the Ising model. And so it's a completely different technique from dimension 3, but it's still relying on this percolation link. And just to give you an idea, Michael proved in 82 that dimensions 5 and more were trivial, and it waited to 2017, so before I was born, and 2017 that we get the 4-dimensional case. So 4-dimensional case is much harder, but it's also much more interesting because that's a dimension in, when we look at physics, right? 3 space and 1 time. Then for magnets themselves, dimension 3 is even more interesting. Time doesn't play a big role there. But then it becomes like yet another order of magnitude harder because, in fact, what allows you to compare it to Gaussian processes in dimension 4 and more, which is what we call the mean field approximation, is just wrong in dimension 3. So physically even, it's very difficult to study the 3-dimensional Ising model, and physicists, like top physicists, have beautiful results, but very partial results on the 3-dimensional case. So, because of course, when you prove continuity, it's just the first step towards the next thing.
We have another question here somewhere in the... Okay.
Well, my first question was that I was interested in this.
Can you speak up a little bit? Oh, here's a microphone
you are
coming.
much closer. You should.
Yes.
Oh, hi. Thanks for your talk. My first question was actually that one, so thank you.
I'm not replying again.
No, yeah, it's fine. But so, another thing that I'm interested in is if you could talk a little bit more, because I kind of lost this part of the talk about the implications of the result you had for like 4-dimensional, the greater or greater than 3, like the theorem showed us,
yeah.
like the implications, and what are the perspectives? So what you can use this result, like what are the corollaries?
Okay, so in some sense, if I understand, why on earth would we care about this theorem? I mean, I'm restating it a little bit more like a 12-year-old would ask. Like, I mean, this is, you know, the lower you get in age, the more extremes they get in questions. It becomes more and more violent. Like, so yeah, I mean, why would you care? In some sense, continuous phase transition, that's the beginning of the story, because there is something beautiful about physics at continuous phase transition, is that you have what we call emergent properties. Emergent in the sense that these are not properties that you would get a priori in your system, but they emerge when you tune the parameter of your system properly, and in particular when you try to get exactly at the critical point. And what happens for the Ising model is that the correlations, for instance, start to have additional symmetries. They get rotationally symmetric, for instance. So if I take a point, I mean, I look at the correlation between 0 and x, you agree that at the lattice level, why would it be similar? I mean, you would expect maybe that it's a natural function of the L1 norm, because that's the graph distance. Well, in fact, at the critical point, no. It's a natural function of the L2 norm. It's 1 over the L2 norm to some power. So it gets rotationally symmetric. These things are things that you expect at the critical point. So in some sense, it was question 2, but question 3 in your exam is, you know, try to get some new emergent properties of your system. And that's exactly what physicists are interested in, because in some sense, these are new state of matter, right? They are things that behave very differently from the other systems, the supercritical or the subcritical one. So these are very interesting properties to try to get. So that's why it's an interesting result, to my opinion. Maybe I should not overextend, but because it's a first step towards the thing. And hopefully the techniques, I mean, as a mathematician, I always like to, I mean, I prefer my proof than my theorems. In the sense, here you hope that the proof itself is giving you hints on how you could prove these additional symmetries, and in particular in dimension 5 and more, the dimension 4, sorry, the property that you have, this emergent Gaussianity that I was mentioning, the fact that you look Gaussian, you can actually see it at the level of this percolation process because the paths in your process are going to start behaving like random walks. So it's exactly the kind of things you want to see. In 3D, this interpretation in terms of path, can you, get a glimpse at the behavior of this path and try to prove, for instance, rotation invariance? But this is a problem for somebody smarter than me. So, I mean, I'm pretty sure in this room we have many candidates, but it's the problem for the future.
Okay, I think we will close the question session here. So let's thank Hugo once more.
Thank you very much.